All right. So, well, I think I might skip the problem session today. Right? It's going to be okay. Thanksgiving. I'm very encouraged with the attendance level for today. It's good. Was Fridays before the break. It's sparks. So. Thanks, guys. But yeah, I won't. So, maybe we want to finish up with some of the sections of chapter 12. Last sections of chapter 12. And sort of rushed through the end last time, but I wanted to kind of mention, what the idea was there. So the idea is that we want to sort of do what we do with integers, but now do it with polynomials with coefficients in a finite field. So use if methods. Define irreducibles in like FP of X. The point is that because FP is finite, right, you can use these methods, right? You can start with your linear polynomials, take all possible products, then you get quadratics, and you'll eliminate the products. In quadratics, you get the irreducible quadratics, take more products, and so on and so forth. Just kind of cross out as you get higher and higher. And then apply proposition that we had last time to find irreducibles with integer coefficients. I see. So this is something that is an easy game to play. And will produce a lot of irreducible polynomials. And it's a good test if you want to say factor a polynomial. One thing you can do is you just say it has integer coefficients, take it mod p, and just check and see for something. That doesn't give you a, if it's not irreducible in a few of these, it doesn't mean that it won't be irreducible over the integers or the rationals, but you have to test sort of all primes, but if it is irreducible at any point, then you know it's irreducible. Okay. So there's one more result, which is actually, and as I think I mentioned last time, it's a really important result, very important result for field theory and Galois theory. But we're not going to get to that. And I'm hoping, many of you are math majors, and I don't know how many of you are considering grad school, but you all should if you're interested in the subject. And if you do go to grad school in math, you will take algebra at the graduate level. And this result will be something that you use, that you should know, because it's sort of very fundamental to sort of field extensions. So let me say what it is. It's a very easy thing to prove given what we've done. The Eisenstein condition. Right here. So what does it say? So it says, let's let f of x equal polynomial with integer coefficients. Yeah, okay. And p a prime integer. Now this looks pretty funky, I agree, but here are the conditions. So suppose when an is not congruent to 0, we'll say not divisible. Two, K is divisible by P. For all K, for all their coefficients. So for K greater than or equal to 0 and less than. But then 3, you look at the 0th coefficient, the constant term. This is not divisible by P, but it's not divisible by P squared. Funky little conditions, but okay. But then we can conclude F is irreducible. And you can say in ZX or in either one. Also say maybe I need to say QX. I am forgetting that I can have some other factor to all of this. Yeah, QX. Other integer factor. All right. The proof is really easy. It's the same trick we're using over and over again. So easy. Well, not so easy, but let me ask you guys. What do you think? How would you prove this? It's sort of the trick we used last time. Well, trick method. Basically, yeah. Right. So what do we do in the previous proposition?
There is some rational number.
Right. No, actually, you're already right. I mean, so that's exactly what I was looking for. We reduce mod P, reduce coefficients mod P. Look in that ring, right? So let's take that and run with it. So let's suppose, well, I'll just say consider F mod P. So consider, you add notation, well, F bar, not to be confused with complex conjugate or anything, okay? Which we're going to talk about in a second. But consider this as an element of Fp of x. What is it? Someone can tell me what it is. Yeah.
AN.
Right, exactly. It's just because of property 2 here, right? All of these other ones are divisible by P, so everything is 0 there. So now, let's suppose for the moment that F can be factored in the rationals. Well, okay, if we can factor it, if it's irreducible in terms of rational polynomials, then by what we've seen in the previous section, it can be reduced as a product of integer polynomials, non-constant. That's kind of what we showed last section. So if f of x is not irreducible, is reducible, then it is in, well, I'll write it down. It is, we have, I shouldn't say it is, sorry. We have f is times h, where these are both integer polynomials, and their positive degree. I mean, I don't want, I'm trying to rule out, one of these being like a prime integer or something, I don't want to just, that's, when you're in Z of X, of course, you can do that, but I'm saying we used last section to say irreducibility of F and Q of X will tell us, or reducibility of F and Q of X will tell us reducible kind of by proper polynomials in Z of X. Oops. 3. It's greater than 0. So just non-constant. Okay, but then we can, going mod P is a homomorphism of rings. There's a homomorphism of rings from Z of X to FP of X. So that means that AN X to the N, which is equal to F bar of X, which is equal to the product of these two, is equal to G bar of X, H bar. Now, both of these have the same degree, right? We have to have, so the degree of G and H add up to N. But that means because AN is not 0 mod P, that the degree of G bar and H bar must add up to N. So these are both also non-constant polynomials here. So since by 1, AN is not equal to 0, so G bar and H bar degrees adding up to N. I'll just say greater than 0. Now, what is the problem? Well, say G of X is equal to Bm X to the M, B naught, and Hx equals C, well, it's going to be M minus N because they add up to, oops, N minus N, sorry. Actually, N. B naught. What can you tell me now? What can you tell me now? Now that I've given a little notation, what can you say? Well, one thing we can say is, this is extraneous, but I'll say it anyway. We can say Pm Cm minus N R equals A. So leading terms. What else can you say? Can you say anything simple? Something amazing. All right, let me ask you a question. What is this ring? A quiz. What kind of ring is it? Does it have any? I mean, okay. FP is fine, but this is I circled the whole thing, but that was just a trick. You're right. FP is finite, but FP of X is not finite. What is FP of X? Do we have any words to describe such a beautiful ring? No words. Huh? It's PID. PID. And what are PIDs? Also, we spent so much hard time. Yeah.
They're UFDs.
They're UFDs.
Wait, is where we're going with this that we're saying that B naught has to be divisible by P and C naught has to be divisible by P, but P naught times C naught is going to be divisible by P squared, like you said.
That's where we're going. Let's get there. That's very astute of you. But you're one step ahead of where we need to be to say exactly that argument. This is a UFD, which means here I've got a factorization of something in a UFD. It's unique. What are the irreducibles in this factorization? It's a unit. It's an element of the field. So what are the irreducibles? Sorry. No, those are factors. 12 is 4 times 3. That's not the irreducible decomposition, right? 4 is not irreducible. So, but, you know, 81 is like, is what? What are the irreducible factors of 81? The prime factor. 3, right? 3 to the 4th. What are the factors of x to the n? Irreducible factors. X. Right? X. So any other factor of x to the n is x to some power. Any other factor. Because you're in a UFD. So what is this? So we can say this. That's one thing we can say. We can also say all BK, CK, well, let's say BJ and CK are 0. I take the residue mod P for all the other ones. So for J less than M and for K less than N minus M, greater than or equals. But these have to be like something x to the power to something with some focus. But now, as John was saying, right, this implies P naught or P divides both. But these are we're assuming these are 2 factors of F, and that means that P squared, sorry, this is notation for, I always use it. Divides by A naught. That's equal to P naught. So that's it. So it cannot be a product of 2 positive degree polynomials. So it's irreducible in QX. All right, so this is Eisenstein's criterion. What can we do with it? So one application, the main application that aside from just kind of like taking some random polynomials and applying it to it, one of the main applications is to prove that cyclotomic polynomials are irreducible. Cyclotomic polynomials are, as I said, they are very important for studying field extensions. Proving they're irreducible over the integers gives you that they're irreducible in all kinds of other contexts. The integers are sort of the, because if you consider any commutative ring or any really ring with unit, you can take 1 and add it to itself all the time, right? If you have characteristic 0, in other words, that gives you a copy of Z, then you always get these polynomials, integer coefficient polynomials when you're working over any ring that's characteristic 0. Polynomials over everything. So this is kind of like working over integer polynomials gives you a lot of general kind of results for arbitrary rings. Okay. The main application, and we won't spend too long on it, but it actually is kind of something I mentioned in a homework session a long time ago, so I thought it'd be kind of fun. Is to consider irreducibility of cyclotomic polynomials. So what is a cyclotomic polynomial? There's actually one for every integer n, and it's sort of a unique irreducible factor of the following polynomial. But I'm going to stick with, well, I'll say what it is for prime, and then you guys can ask me if you want that. So for prime p, integer prime p, if p of x, well, it's this polynomial x to the p minus 1 plus x to the p minus 2. Excellent. Very simple polynomial. And you have a simple equation that will say, okay, if I multiply this times x minus 1, I get x to the p minus 1. Now, let me just make a comment. So our goal really, which is going to be an easy goal to accomplish in a minute using Eisenstein Criterion, is to show that this is irreducible for any prime. Now, why would you want to know that? Well, it's often important to know whether or not you can get roots of unity. In other words, whether or not you can solve an equation that looks like x to the n equaling. Can you find solutions to this besides one? And of course, you know, well, or if you don't know, if you look at the complex numbers, those roots of unity, they appear on like the unit circle, sort of evenly spaced. These are very important geometric and algebraic numbers. And if you're interested in the algebra of them, you can extend your field by taking, say, rationals and modding out by this polynomial. This will give you your pth roots of unity and will extend your field. But of course, if you want this to be a field, you need to know this is irreducible. Otherwise, it's not a field. It's something funky. But this is sort of where it's going. This is why you want to know this, mathematically speaking. And then there's all kinds of like little fun games. So you can get like the rationals with like the Weierstrass rationals and so on. But why is this irreducible? So theorem. This is irreducible. In x. Okay, well, we know that this is a primitive, a polynomial, integer polynomial. And so we just need to show it's irreducible in cubes. And for that, we can use Eisenstein's criterion. But we're not going to use, it would be hard to use Eisenstein's criterion on this polynomial, right? Because I can't find a prime that factors any of these at 1, that's not going to work. So it's kind of funky to think that. But then you remember way back in the day when I was going on and on in a review, I started drawing Pascal's triangle a ridiculous number of times. Take a x equaling y plus 1. Consider consider the cyclotomic polynomial now as a function of y. Basically just shifting your line over. And what are you going to get? Well, you're going to get y, looking at the y here, already it's y times b y plus 1 is equal to y plus 1 minus 1. I'm just writing this to see where I'm getting the y factor. This is equal to y plus 1 p minus 1. How do you remember that exercise? You have the expansion in terms of binomial coefficients of the power, right? So y to the p plus p choose 1, y to the p minus 1, plus p choose 2, y to the p minus 2, plus p choose 1, y, plus p choose 0, which is 1. That's this big power expanded, right? I'm minusing 1. Whoa. Subtracting 1. Something like this. So those cancel at the end. Now you remember the exercise? Or I don't know, remember the rant that I went on about you take a prime and you look at the Pascal's triangle and you look at the pth row. You guys remember that? I have a distinct memory of that. I remember all of my rants, at least within like a 3-month lag. Then I forget completely what I ranted about. So it's easy to forget, you're saying. I should rant like, I should rant less, or I should be more ranty. That should be more funny. That's harder. Okay. Yeah. Nobody remembers? I feel like you remember it happening. The content. I showed you guys the beautiful pictures from like the yeah, there's all kinds of fractal stuff. This is like you do this. So I teach like every once in a while the math circles. This is a Russian thing where you take elementary school kids and subject them to beautiful math. So we have like there's some nerds in Manhattan, Kansas. So mostly foreign who come and like bring their kids and they want their kids to learn stuff. And so we just spend a lot of time talking about math. But anyway, this is one of the things we do. We like they break out crayons, we draw Pascal's triangle, and then we reduce them on P. Right? We get all these beautiful pictures. So if you remember, I mean, I don't want to redo it. Probably can go. I don't know. The point is if you look at the pth row, mod P, and you take a look at the Pascal's triangle, you'll see a bunch of zeros. This is divisible by P. This is divisible by P. All of these are divisible by P. Except for, of course, 1 here. So what you'll get is y to the P plus, something divisible by P. Nothing. Well, this is P in this case. Sorry. Here you get something divisible by P. I don't want to, I'm just going to write it this way. Sometimes, whatever. We know what it is, but okay, I'm not going to write it. But I do want to write the last one. This is just P. That's just P. If P choose 1 is P. I should have said P choose P minus 1. They're the same, but okay. Now, the point of me writing now is, of course, I've got this factor of y. So I can divide both sides by y. And if I do that, and do it. Oh, a lot of brands. Rough. All right, here you go. Now we look at the coefficients, and now we remember Eisenstein. We feel great. We look at the coefficients here. We've got P divides all of these coefficients. Of course, it doesn't divide 1. And furthermore, we look at this last coefficient, and it's just P. So P squared does not divide the last coefficient. And so that tells us, by Eisenstein, that tells us that this is an irreducible polynomial in Y. Of course, just a change of variables tells you that it's irreducible in X. If there was a factorization in X, there'd be a factorization in X minus 1. Pretty cool stuff. Pretty cool stuff. All right, in the last 20 minutes, we're going to have a little fun. Look at the last section, which deals with Gauss primes. Very nice, very, very fun. This does not have, mean, you can go your whole life without knowing this, as most people in the universe do, or at least in the Earth, I don't know, but at least, you know, consciously. I don't know. Maybe people know about this stuff. They don't know it. They know. Probably not. They probably just don't. You know, you've like read articles, not to rant again. You've read articles about like, you know, like how dogs know calculus or something. All that kind of stuff. They're like motion. They analyze how animals move, and so you know, but you don't know. Like my dog never told me anything about that.
You don't speak dog.
Right. Right, I don't. You're right. I don't speak dog. No. No, I tried to teach her chess a little bit. It didn't work out. I figured if I could teach my dog chess, I could be like, you know, to kids that. So I go to elementary schools and help with chess every once in a while. We're trying to make chess a thing. That's what I'm on. Yeah. Anyway, I figure if I could tell the elementary school kids I could teach my dog chess, that they would have no excuse. They'd be like, okay, well, the dog can learn. And the dog's too. So yeah. Anyway, that was not at all relevant. Let's talk about Gauss primes. So we want to look here, right? Zi. We want to know about prime numbers here. Prime Gauss primes, prime elements. You might say, that's boring. I don't care about Gauss primes. And I'll say, okay, well, you know, maybe, I don't know, probably right. Because you know about primes, right? And why are, okay, so there's some new primes, right? There's some new prime elements, big deal. But I want to say, no, you're right, there are new prime elements. But you don't know primes anymore. Do you? Like 2? Not prime anymore. Not prime. So, okay, you get some new primes, and now a whole bunch of old primes are gone. They're not prime anymore. So what's going on? Moreover, you might be interested in saying, okay, is it the case that some factorizations give you something interesting? You might say that. I just said. So for example, let's say suppose C is an image. And let's say we consider it square. Well, let's say, can we find a nice factorization? This factorization is a kind of a cool factorization. This is a Gauss prime. Let's call it, I don't like to use the letter pi for these. And this is its conjugate. You guys know conjugates? Complex numbers? I've told you, I've talked about it. Like just take a plus bi, you turn it to a minus b. So you could ask, well, let's say is c squared equal to pi times a conjugate? Well, if it is, then I can write pi equals a plus bi. It's a Gauss number, right? And if it's equal to such a factorization, then this is a plus bi times a minus bi. What's that equal to? A squared plus b squared. This is a Pythagorean triple, right? It describes the sides of a right triangle. You can ask, you know, what are all possible factorizations? That's all possible integer side lengths of a right triangle. You can start asking kind of questions about relating some of the algebra we're doing to is some kind of really basic geometry that you see quite a bit in just like, from elementary school on. So some of this stuff is kind of interesting, kind of fun. This is where I would say maybe people have seen this before, but they don't know. But here, what we want to do is we want to prove this theorem. We'll go through some of it, maybe all of it, I don't know, which really characterizes what the Gauss primes are. Well, at least what the Gauss primes are when you think of them as integers, like which integers stay prime in the Gauss. Who doesn't? But here's the theorem. So it's several parts, it's a bit long, and the proof is even longer. Okay, so first it says, okay, suppose pi is a Gauss prime. And let's consider this conjugate, pi bar, it's complex conjugate. Then one of two things happens when you consider pi times pi bar. It's either prime integer, either a prime integer, or a prime integer squared. Okay. Now let's look at the other side. Let's suppose we take one of our prime integers and think of it inside of the Gauss integer. Suppose p is a prime integer. Then either p is a prime, is a Gauss prime. What's prime is a Gauss? No. Or a p is equal to something like pi times pi bar, or some Gauss prime. But it factors into Gauss prime. Right? T gives us this definite answer to what stays prime. So the integer primes are also Gauss primes. Are all primes P that are congruent to 3, 9, 4. So you can list them. You can list all primes up to a certain point. So for example, 5 is not among them. But you already knew that, because you know there's a 3, 4, 5 triangle. Like 7 is prime. So this C actually is an immediate consequence of D, which is where Arden gets a little, it's going too far. It's got too many sub theorems within the theorem. All right. So I'm writing it down. So don't blame me. P be an integer. Following our equivalent. When B equals pi times pi bar, or some Gauss prime pi, let's call it GP. Two is congruent to 1, not 4. Or P is 2. There's this possibility. P is the sum of two integer squares. The residue of, okay, so this is, so I'll write what he writes and I'll explain that. It says the residue of -1 is a square of P. And what that means, if you are trying to untangle it a little bit, is it means there's a solution. The following equation of P is just x squared. So saying this, it's a square in that. Long theorem, not too hard to prove. This last part, D, takes a second. But we can do probably get through A and B. He's kind of fun though. I like D with those. This is a pretty satisfying theorem, I gotta say. If you have a theorem where you kind of get complete classifications like this, kind of nice. All right. Who wants to help me with A? I got a Gauss prime pi. I take pi times pi bar. I know it's an integer, right? Because this is like a squared plus b squared. This is an integer. Being an integer, I do have factorization in integers. So I can write it as a product of primes, integer primes. What can someone tell me about R? Remember, the key guiding wonderful thing, we want to use what we learned, right? We learned that Gauss integers form a Euclidean domain, which is that smallest circle inside of that Venn diagram. It's a PID, in particular, it's a UFD. So we talk about factorization and unique factorization. We're talking about elements that got that, here we have pi times pi bar. We factor it into a bunch of other factors. But pi and pi bar are prime. If pi is prime, pi bar is prime. That's not hard to do. Yes. So what can you tell me about R? R can be 2. Can R be anything else? 1. Right? It can be 2 or 1. It can't be more. This is the prime factorization. 2 Gauss primes. These integer primes may or may not be prime. I don't know. But what we do know is that there are most 2 prime factors of whatever this Gauss integer is. And so there can't be more factors than 2. So since UFD pi bar prime, or irreducible, however I mean, they're the same thing in UFD, irreducibles are primes. R is less than or equal to 2. R is 1, done. Done. Right, because let's reread what A is saying. It's saying if we have this situation, then this is either prime integer. Say prime integer. I could say prime integer, or it's a prime integer squared. Okay, so we need to show if it's not, if R is equal to 2, then P1 and P2 are the same. If pi bar equals P1, P2, well then we have two factors, and pi1 and pi and P1 must be associates. PDF. This is a unique factorization domain, which means up to some ordering, some shift, or some reordering. Either pi and P1 are associates, or pi r and P1 are associates. Let's just reorder if we have to. The pi either P1 or P2, but let's just choose P1 are associates. What does that mean? That means that pi P1 is a unit times pi. And what are the units of the Gaussian integers? What are the units? Yep. This is either plus or minus P1 or plus or minus I. But in either of those cases, we see that pi and pi bar are also associates. Right? If you're on the real line and you take the conjugate, then you're still on the real line. If you're on the imaginary axis and take the conjugate, you're negative. So this means that pi bar, they're the same. They're also associates. So everything is P1. Right? So P2 has to also be associated. And then you just have that since it's an integer, it's a positive integer, it must be P1. It's P1 times P2 since it's a positive integer, it must be P1. I don't know. I'll say P1. Sort of plus or minuses. It could be that, yeah, they have to be. They can both be negative. I guess I could have P1 equals. No, I'm not. I assume they were both positive. Sorry. For B, it's sort of the opposite. P is a prime integer, then either P is a Gauss prime or P equals okay, so B is not too bad. So let's take a look at B. So factor P in the Gauss integers. So I'll have some integer factors, and I'll have some Gauss prime factors, like guys that have, that are not integers. But now I mean, there are a lot of things I can do. I can also, so I can do the following thing. This is irreducible. This is my prime factorization, or irreducible factorization that I'm writing. Okay. I can take then, this is also equal to P bar equals P1, QR, I1, bar, IS. Since it's unique, okay, well, since it's unique, that tells you that I can find a bar amongst these factors. Right? So that means that these guys come in pairs, a pi and a pi bar. So this tells me that I get something, I'll be done in just a second. You are pi 1 bar, pi, okay, I don't know, like, call it, pi t. But now we've got, each of these is an integer. P is prime is an integer. So that means there's only one of all of these. So if it's an integer, then it's P is just a prime and it's irreducible. It's Gauss prime, doesn't have any other Gauss prime factors. If it's not a Gauss prime, then it's going to be one of these products. Okay. All right, guys, have a really great week off. And I will see you Monday after.
Is there a C for the Gauss primes?
Yeah, I mean, I think you can do this for, yeah, definitely. I think you can do this kind of for discrete Euclidean domains, for like, arithmetic rings. You can do this kind of a thing that are also Euclidean domains. Just kind of do it with respect to norm, essentially. Keep on going.
Might have to make Python find me a list of